Dynamics. This unit is all about forces. It's very similar to kinematics where we're looking at motion, but now we focus on how forces cause or restrict motion instead of just the actual motion of acceleration and distance and speed and stuff like that. So we're going to start with Newton's three laws. These are kind of the basics of all force stuff in physics that you do. So a little bit of history. This is about as much history as we'll do in this course. Isaac Newton, he was born on Christmas Day, December 25th in 1642. He was the one who came up with his three laws that really are the main ways that we govern how motion works. They show up in all realms of physics. You just can't get rid of them. Before Newton, there was Aristotle, like way back, like 300 BC. He knew that force could move an object. He talked about natural and violent motion. The big thing with Aristotle is he thought that heavier objects fell faster, which is not true. We know that's not true, but back then, and for hundreds and hundreds of years, that's what people thought. Until Galileo came around in the kind of mid 1500s, and he was able to actually prove that all objects fall at the same rate. Which was a huge step forward in science because before that we thought everything fell at the same rate. Galileo did a lot of cool things. He was a huge influence on science and math. So if you're interested, you can look him up. Another kind of cool thing is Galileo died in January and then Newton was born in December. So they kind of passed the torch off to each other, and Newton really took everything that Galileo had come up with and took it a step further and came up with his three laws. So what are his three laws? The first one, an object continues to be in a state of rest or uniform velocity in a straight line as long as no external force acts on it. That's a lot of words for saying objects are lazy. I like to call this the lazy law or the law of inertia because this is saying that if an object is moving, that object or staying still, that object wants to stay doing whatever it's doing. It does not want to move. It resists change. Just like when you come home from a long day at school and you go lay down on the couch or on your bed, and maybe someone says, hey, you know what, go clean your room, go do this, go do that. You're like, no, I don't want to get up. That's the same thing. You resist motion. Once you are laying down, once you're doing something, you don't want to change. That objects follow that same thing. Now, if we were in person, I would do this experiment with a coat hanger. I'm not going to do that. We're just going to pass that. Okay. But really, like the big thing with this law is that it tells us that if an object is moving, that means that a force must have acted on that even just for a brief time. And if that object is still moving, you've got two options. Option one is that force is still acting on it. But option two is there's no friction, there's no resistance, there's nothing slowing it down. So just a small little initial push will make that object move on forever. Kind of like in space. If you kind of slowly push yourself away from the space station, you are going to drift forever away from the space station because there is nothing slowing you down. As long as no other forces act on it, that object will continue to move. Okay? Now, there's a big thing with mass versus weight. Okay, when it comes to this first law, students also confuse mass versus weight quite a bit. Now, if you think about kicking a can full of cotton balls, it's probably not going to hurt that much. But then if you kick a can of steel nails, well, what's going to happen, right? I think it's pretty safe to say that the steel nails is going to hurt more. Is that because it has more mass or because it's more weight, right? Now, because a lot of times students think that mass is the same thing as volume, but it's just not, that's just not true. Both the same volume of cotton balls and nails, that the volume has nothing to do with it. The nails are there's more to the nails. The nails have a higher mass, which means that mass doesn't want to move and that's going to hurt more. Okay? If we have something that has more mass, we say that object has more or greater inertia or the ability to resist motion. The more mass something has, the less it wants to change. So when we're talking about how much matter an object has, so how much of there actual is an object, how much mass there is, that's the inertia of this object. The weight is related to the mass, but it's a measure of the force of gravity acting on the object, which means weight depends on not only the mass of the object, but also the location of the object. Is that object on Earth? Is that object on a different planet like the moon where gravity is less? Where is that object? The weight will change based on where you are, but the mass will always stay the same. If you are 75 kilograms and you are on Earth, you are 75 kilograms on Earth, but you are also 75 kilograms in space or on the moon. You are not losing any of your mass when you go into space. But when you're on the moon, the acceleration due to gravity, that force acting on you due to gravity, is much, much less on the moon than it is on Earth, which means your weight on the moon is much, much less because there's less force acting on you. Still the same mass, but different weight, okay? And that kind of lends itself a little bit to this question is, how much force does it take to move an extremely heavy object in space? This answer might surprise you. Think about it, we'll go over it in class, but how much force does it take to move an extremely heavy object? Okay, in space where there's no resistance. Okay, the big thing, mass and weight cannot be used interchangeably. Okay, they are not the same thing. One is measured in kilograms, one is a mass. The other one's measured in newtons, and it's a force. So do not get those confused. I would strongly suggest you scan these two videos. They're short, they're like 2 minutes each. Watch these two videos that really talk about the difference between mass and weight, and then how inertia has to play into that, okay? So there's some questions here. I want you to try these questions. We'll go over the answers in class, but I want you to go through these questions, jot some things down, and see what you think. The second law of motion, this is probably the most important law that we're going to do in this unit. And this one says, if there's a net force acting on an object, the object will experience an acceleration based on the formula mass times acceleration, F equals ma. You probably saw this in grade 10 quite a bit, but in grade 11, we're going to take this a step further, and you need to understand how this formula works. We're going to use this over and over and over again. This is going to be a brief introduction to it today, but this is going to be the main focus. We're going to use this law over and over and over again in this course. So really what we're talking about when it comes to motion is we're talking about if there is a net force, not just one force, because we can have multiple forces acting on an object, but what we care about is either what the sum of all the forces is acting on an object. If we do not have a net force, we do not have a change in motion. But if we have a net force, we are going to get a change in motion. So if you think about tug of war, if both sides are exactly equal, the rope doesn't move, right? You're just locked in the middle. But as soon as one side gets tired, you get an imbalance of force. You get a net force moving in one direction, which means you get that rope starting to move in the direction that has the greater force. Now, in order to kind of visualize this a little bit more, I want you to scan this. This is a little online simulation where you get to play with net force. You get to play with vectors and stuff. So this works on your phone, computer, whatever you want. You can click on that link, but I want you to go scan this link and play with the simulation to just play with what a net force means. Okay, and then just do a quick little sketch. What did you learn from this animation? What did it teach you? Okay. So some quick examples of what net force looks like and how we can use this to do some calculations. If you've got you and your friend both pulling on a rope horizontally in the same direction, each with the force of 5 newtons, what's the net force on the rope and which way does the rope move? So if we just kind of sketch out a box, because everything in physics kind of turns into a box, and if we've got 2 people over here pulling on this box, okay, there's one, there's the other one, that's fantastic. And we've got 2 ropes, like so, going like that, like so. And each of these ropes, each of you and your friend are pulling with 5 newtons, then we can say that the sum of the forces acting, or the net force on this box, is probably going to be 10 newtons. right? And that 10 newtons is going to act to the right because you're both pulling to the right. And what that means is that the rope is going to move to the right, okay? Not really anything too crazy here, something that we've seen in our daily life over and over and over again. But what happens if I'm fighting with someone over an ice cream cone? So I'm going to pull left with 15 newtons, and the student pulls right with 7 newtons. What's the resultant net force on this object, and which way does the cone move? So if we draw a nice, beautiful ice cream cone. So obviously this is mint chocolate chip strawberry ice cream with some cookie dough on top. So obviously that's the best type of ice cream. But really more importantly is if we've got a student pulling to the right with 7 newtons like this, and me trying to win this ice cream cone pulling it to the left with 15 newtons, well, the winner, right? If we talk about net force here, well, obviously I'm going to win. The net force, if we want to say, we could even use this 7 minus 15 because we're going to the right 7 and then to the left 15. Well, 7 minus 15 means it's going to be negative 8 newtons, or to the left. Now, if this reminds you a lot of vectors, well, yeah, these are just vectors. All this is vectors, and which means this thing is going to move to the left because I am going to win this ice cream cone and eat it because I am the best. These things, like I said, are called free body diagrams. We're going to do a whole big thing on free body diagrams, so don't really panic about that. But the idea here is that if you have a net force, that will create motion, right? A net force on an object will create motion, and we will use this formula, F equals ma. This little big E thing in front of that means sum. We will go over that a little bit more, but so really that's sum, and that's exactly the same thing as the net force. I like using sum better just in terms of terminology, but I use both interchangeably. Okay, so this is just a brief introduction on free body diagrams and stuff like that. We'll do more of this a little bit later. The third law of motion, for every action, there's an equal and opposite reaction, or every action has an equal and opposite force pair. This just means, right, everything has consequences. If you hit your hand on the table's gonna hit your hand back, that's why it hurts. If you've ever been on a boat or something floating in the water or something, if you jump off it, you move one way, and well, I mean, the boat's going to go the other way, right? It's an action reaction. These show up all over the place. A really good video here. It's only like 3 minutes of what this law looks like in space. And then once you watch this, I want to try this. I want you to try this on Earth. See if you can get a rolly chair, something rolling so there's very little friction. Throw a big object, see what happens. Okay, we're not going to do too much with Newton's third law, but it is important to know what it is. Okay, so those are the 3 laws. Go through these notes, try some of these questions, and then we'll go over very briefly in class to make sure that everything is all good. Because you need to have a kind of a conceptual idea of what these 3 laws are and how these forces work when we move forward into this unit and start doing some math with this stuff.